So in this class, we will see amplitude modulation. So let us consider a carrier signal AC cos 2 pi fc t. So here we are taking pi value as 0 for simplicity purpose. So we are only considering the amplitude and frequency. So the carrier will be AC cos 2 pi fc t. So amplitude modulation is defined as the process in which amplitude of the carrier wave is varied linearly with the message signal. So since we are varying the amplitude of carrier in accordance with the message signal, it is called as amplitude modulation. So coming to the time domain description of AM wave. So the standard form of AM wave is defined by this equation. St equal to AC into 1 plus Ka m of t into cos 2 pi fc t. So here in this equation, Ka is a constant called amplitude sensitivity of the modulator. So if we observe this equation clearly, we can observe this factor. So here instead of amplitude AC, it is multiplied by this factor 1 plus Ka m of t. So the amplitude of this carrier wave is varied according to the message signal. So since the message signal is varied with time, this amplitude of the modulated signal will also be varied according to the message signal. So here this factor is called as envelope of the AM wave. So the amplitude of the time function, so this amplitude is depending on time. So the amplitude of the time function multiplying this factor cos 2 pi fct is called the envelope of the AM wave. So it is denoted by A of t and is given as AC into 1 plus Ka m of t. So this factor is defined as the envelope of the AM wave. So this factor magnitude of Ka m of t into 100 is called as percentage modulation. So depending on the value of Ka, we have three cases in amplitude modulation. So if this magnitude value Ka into m of t is less than 1, then AM wave is said to be under modulated, and if its value is equal to 1, then AM wave is said to be critically modulated, or we can also call it as 100% modulation. And if this magnitude is greater than 1, then it is called as over modulated AM wave. So these three cases will depend on the value of Ka. So if we see basic AM waveform, so this first plot represents the low frequency message signal. So if we observe this, the frequency of this message signal is very low. And this second waveform is the carrier signal, which is having higher frequency when compared to the message signal. So in amplitude modulation, what we do is we vary this amplitude of the carrier in accordance with the message signal. So this third waveform shows us the amplitude modulated signal. So this red color waveform represents the carrier, and this blue waveform will represent the message signal. So as I said, this is called the envelope of the modulated signal. So this blue waveform represents the envelope of the modulated signal, and this peak value is the maximum amplitude, and this is the minimum amplitude of the AM wave. This is the maximum amplitude and this is the minimum amplitude. So here we can observe from the figure that the amplitude of the carrier, that is this blue line or envelope, is varied in accordance with the message signal. So once this modulated wave is obtained, so from this message signal can be easily tracked by tracking the envelope of the AM wave. So if we consider the envelope of the AM wave, we can easily track the message signal. So at the receiver side, we use an envelope detector. So it will track this envelope waveform, which will give us the message signal. So this is the basic AM wave. In order to see these three different cases, we'll take some example values for these AC, KA, and M of t. So in the first example, let the value of AC be 1 and KA equal to 1 by 2, and M of t is the message signal, which is taken as cos 2 pi fmt, and the frequency of this message signal is taken as 1 by 2. So after substituting these values, the envelope will become A of t equal to AC into 1 plus KA M of t. So here AC value is 1, KA is equal to 1 by 2, and this cos 2 pi fmt, Fm is 1 by 2. So this 2 and 1 by 2 will be cancelled out, and this term will become 1 plus 1 by 2 cos pi t. And the modulated waveform becomes St equal to 1 plus 1 by 2 cos pi t. This is the envelope, and this is the carrier signal, cos 2 pi fc t. So now in order to plot the AM wave, so the part in this bracket will give us the amplitude values. So in order to plot this waveform, first we will calculate the maximum amplitude and minimum amplitude. So we already know that the maximum and minimum values of cos function are plus 1 and minus 1. So the maximum value becomes 1 plus 1 by 2, which is 3 by 2, and minimum value will be 1 minus 1 by 2, which is 1 by 2. So the waveform will be changing between this maximum and minimum values, that is plus 3 by 2 and 1 by 2. So now as the amplitude is varying according to this envelope, and this is the carrier. So this will be the resultant AM wave. So this green curve represents the envelope of the carrier, which is 1 plus 1 by 2 cos pi t. So this is the case where Ka value is less than 1. So here this waveform, there is no problem in this waveform. Now let us consider another example where Ka value is greater than 1. So in this case, we have taken Ka is equal to 3 by 2, which is greater than 1. So in this case, the envelope becomes 1 plus 3 by 2 cos pi t, and this is the modulated waveform. So now in this case, if we again calculate the maximum and minimum values, so the maximum value will be 1 plus 3 by 2, which is 5 by 2, and the minimum value will be 1 minus 3 by 2, which is minus 1 by 2. So now the envelope will be varying between plus 5 by 2 and minus 1 by 2. So this will be the envelope, and considering the mirror image, the waveform will be like this. At this point, so where the envelope is crossing the 0 point, so since the amplitude is suddenly changing from positive values to negative values, the phase of the carrier will be shifted by 180 degrees. So the same figures are shown here. So this case is when the Ka value is less than 1. So here, since the maximum and minimum values are both greater than 0, so there are no zero crossings over here, and the modulated waveform looks like this. But in the case 2, when Ka value is greater than 1, so the minimum value will be less than 0, that is negative value. So here in such cases, the envelope will be crossing 0 values since the minimum value is less than 0. So at these 0 crossing points, since the value is changing from positive to negative values, the phase of the carrier will be shifted by 180 degrees. So these phase reversals will cause a distortion called envelope distortion. So if we observe these two figures, from this wave we can track this envelope and we can get the message signal. The message signal can be traced from this envelope. But if we see this envelope, the envelope will be like this. The actual envelope is this one, but due to this over modulation, the envelope that will be traced at the receiver side will be like this. So this is not the message signal, but the distorted signal. So this error is called as envelope distortion. So again, the three cases are shown here. The three cases are shown here as we discussed earlier. That is Ka m of t less than 1, equal to 1, and greater than 1. So this is the under-modulated case, this is critically modulated case, and this is the over-modulated case. So here, if we observe, when magnitude of Ka m of t is less than 1, this minimum value will be above the 0 value, and hence by tracking this envelope, we can obtain the recover the message signal at the receiver side. And in this case too, when modulation is 100%, that is when magnitude of Ka m of t is equal to 1, so this minimum value will be exactly 0. So even in this case, there will not be any distortion because this minimum value is not crossing the 0 axis. So even in this case, by tracking this envelope, the message signal can be recovered at the receiver side. But in the case 3, that is over modulation case, whenever the magnitude of Ka m of t is greater than 1, so the minimum value will be negative value. So in such cases, there will be 0 crossings since the minimum value is negative. So whenever there are 0 crossings, there will be phase shift of 180 degrees at these points, and hence there will be a distortion in the envelope called as envelope distortion. So here from this case, if we track this envelope, the waveform will be obtained like this, which is not the message signal. The actual message is this one, but by using envelope detector, the tracked signal will be this one, which is not the transmitted message signal. So this has been occurred due to the phase reversals, and this distortion is called as envelope distortion. So whenever the value of Ka m of t is greater than 1, the modulated wave will suffer from envelope distortion as it is over modulated. So in order to avoid this envelope distortion, this percentage modulation should always be less than 100, or this Ka m of t value should be less than or equal to 1. Only then we can avoid these envelope distortions. I will again repeat these slides. So here, depending on the value of Ka, so we can divide this AM wave into 3 different cases. So if this magnitude Ka into m of t is less than 1, then AM wave is said to be undermodulated. If it is equal to 1, then it is said to be critically modulated, and if it is greater than 1, it is called as over-modulated wave. So if we see the basic AM wave, so this is the low frequency message signal, and this is a high frequency carrier signal. So now, since we are changing the amplitude of the carrier in accordance with the message signal, so this will be the resultant AM signal. So here we can see the amplitude of the carrier, that is this blue waveform, is changed in accordance with the message signal. This blue line is nothing but the envelope of the AM wave, and this red part represents the carrier signal. So the amplitude of this carrier red waveform is changed in accordance with the message signal. And then we have seen 2 different cases. One is what happens if the Ka value is less than 1, and the other case if Ka value is greater than 1. So if Ka value is less than 1, so this envelope function, that is 1 plus 1 by 2 cos pi t. So here in this case, the maximum value will be 1 plus 1 by 2, which is 3 by 2, and the minimum value will be 1 minus 1 by 2, which is 1 by 2. So the envelope will be changing between 3/2 and 1/2 continuously. So here in this case, there is no problem because this envelope is not going below the 0 axis. So from this waveform, the envelope of the carrier can easily give us the message signal. But on the other hand, if we take the Ka value as 3/2, which is greater than 1, so here in this case, the maximum value will become 1 plus 3/2, which is 5/2, and the minimum value becomes 1 minus 3/2. So since the minimum value of cos function is -1, so 1 minus 3/2 becomes minus 1/2. So here in this case, the envelope will be changing between plus 5/2 and minus 5/2 continuously. So here the problem here is that the envelope will go below the 0 axis. So hence, when the waveform is going below the 0 axis, since the amplitude is suddenly changing from positive value to negative value, the phase of the carrier will be shifted by 180 degrees. So if Ka value is less than 1, there will not be any phase shift in the carrier. But when Ka value is greater than 1, there will be a phase shift in the carrier signal. So these phase reversals will cause a distortion called envelope distortion. So if we see all the three cases here, if Ka, magnitude of Ka m of t is less than 1, so it is the under modulation case, and if it is exactly equal to 1, so the waveform will look like this. And for over modulation case, that is Ka m of t is greater than 1, so this envelope will cross the 0 axis and there will be some phase reversals at these 0 crossings. So when the magnitude of Ka m of t is greater than 1, this modulated wave will suffer from envelope distortion. So in order to avoid this envelope distortion, this percentage modulation should always be less than 100%. Because if we don't choose the value of Ka less than 1, so when we track the envelope from this waveform, we cannot get the exact message signal. So in both these cases, we can track the exact message signal from the envelope. But in these cases, in the third case, the envelope will be tracked like this. Actual envelope is this one, but due to this over modulation case, the envelope will be tracked like this. So which is called as envelope distortion. So always this percentage modulation should be less than 100, or Ka m of t should be less than